diamonds are a very, very, of course, valuable gem. And in fact, we can say a lot about diamonds. This table right here, in fact, gives us the weight, which in diamonds are weighed in carats, and the actual value. And here is what we want to do. We want to find an exponential model for this data, and then use the model to estimate the weight of a diamond that's worth about $6,000. So you can see the table sort of ends right before 5,000, but assuming that this data is going to be modeled with an exponential function, the question is, can we find that function, and then can we use the function to then extrapolate and say what's going on when we have a $6,000 diamond, what would its corresponding weight be? Okay, well, a wonderful way of dealing with this sort of complicated diamonds data is to actually take out a computer or a graphing calculator and actually use it to produce what's called exponential regression in order to figure out what is the exponential function behind the data. So exponential regression means trying to fit the data with an exponential function. So how would you use the graphing calculator to do this? Well, we have the data, and the first thing we do is we enter each of this information, this data, and this data into two lists. So we enter that into two lists, and then we would actually do an exponential regression to get the equation. And so the equation would look like for this data, if you were to plug it through, and I'm doing it there live so you can actually sort of see how it would look for real. But the thing we would get, and I should use a diamond color, or it's purple, would be that the value, given the weight, would be 935.67 times 1.52 to the W power. Okay, now, where do we go from here? Well, what I want to do now is I want to see when, in fact, what the weight is when this value here, when the value is equal to $6,000. So I want to make this $6,000, and I want to find out what W is going to actually make this equal 6,000. So we've seen this before. What we do is we'll call this W1. So we'll enter this function for W1, and then we'll actually enter the constant function for for Y1. So we call this Y1, this function Y1, and then Y2 on the calculator will be the constant function 6,000. And then we just graph them, and we look for the intersection. Now, I want to show you the graph of them. So here is the graph of them. Okay? And then what we want to do is we want to adjust the window to see the point of intersection. And you can see that point of intersection right there. And now we can actually find what the value for W is at that point of intersection. And if you read off there at the screen, you can see it. We see that it's approximately 4.44 carats. And so there's the answer. So you can see the power of the computer actually really allows us to focus in on even diamonds. Even diamonds. Cool. Okay, following an exponential function, because they have a half-life. If I have so much now, then in a particular fixed time period later, like maybe a year later, I'll have half as much, which means a year later, I'll have half of what I currently have. And a year later, I'll have half of what I currently have. And that actually is describing exponential decay. Here's another example, which actually is more in line with what we might actually see in our everyday lives. So the value of a truck bought new for $32,000 decreases 16.5% each year, and our mission is to write an exponential function, graph it, and then using the graph, try to predict when the value will fall to $2,000. So let's take a look and see. Well, we have exponential decay, which means this is the formula we want to look at. Notice the difference now is that we have a negative sign here because things are decaying. And let's go. Decay. So I'm going to use a decaying color. I'll use red. So f of t in this case will be the initial amount, or in this case the initial price of the car, $32,000, times 1 minus the constant rate, which is 0.165 all to the t power. Okay, and now we'll use a graphing calculator to actually produce a fairly accurate rendering of the graph of this exponential decay. that's fine. Then we have to set the window. So setting the window involves us thinking about the max for x, the min for x, the scale, and the same thing for the y's. So if we think about this, we can figure out probably what we want for x. Well, so for x, let's have it go from 0 when we start to, let's say, 20 years with a scale of, let's say, 5. And y min, well, we'll start at 0, and we'll go up to basically a little bit more than the value of the car, which let's say is 33,000. Now, of course, we actually want to find out when we're going to actually go to 2,000, so we could actually have even a higher min if we want, but it doesn't really matter. Let's have the scale go, the y scale be 1,000. Okay, so now, when we enter in the equation, we can actually see the graph. Turn it on, and you can see the graph. So now we're looking at the graph of the function, and you can see the exponential decay happening there. And then if you push the trace button, we can use these two arrows here to go up and down and move that crosshair right along the curve, and we can actually line it up so we can have the y value be approximately 2,000. Once we have that y value, we can look down and we can read off exactly what the x value is. And in this case, what we see is that x, or in our language, t, equals 15.4. So that means that we have to wait about 15.4 years, or approximately 15 and a half years, for the truck, which we originally purchased at $32,000, to actually fall in value to be worth about $2,000. So we've got about 15 and a half years to go, and we were able to conquer that question using exponential decay. The exponential function is probably one of the most important functions that's around us in our everyday lives. When you're growing physically, when things are decaying, when interest is being accrued, when bacteria is taking off, when radioactive substances are slowly vanishing, they all conform with an exponential function, min. So, suppose that you win some contest, and the people that are running the contest offer you two options for your prize. One option is to receive a $25,000 brand new, fancy, shiny, waxed car. Really great. Now, maybe you don't drive yet, but maybe they'll even provide a chauffeur, who knows. Anyway, so there's that prize. And then the other prize is sort of modest. They'll give you a penny. They'll give you a penny. And then the next day, they'll give you 3 times that. So they'll give you 3 pennies. And then the next day, they'll give you 3 times that. And so you'll get 3 times 3, 9 pennies. And you keep doing that for a month. Which prize do you pick? Shiny car, the 1 penny. Well, when you first think about it, you're like, whoa, I'm going for the car. Well, let's actually do the math and see what's really going on here. The answer may be surprising. So let's make a little chart where we have the various days and the amount that we get. So the first day, with this penny option, we get 1 penny. The next day, we get 3 pennies. And on the third day, we get another 3 times what we previously got, which would be 9 pennies. Okay, now, do we see a pattern? Well, let's think about it. I notice that each time I'm multiplying by 3. So I can actually write this number as 3 to the 0 power, which if I want to write that sort of in sympathy with the fact that we're at day 1, I could write this as 3 to the 1 minus 1. Okay, what about 3? Well, the number 3 I could write as 3 to the first. And how could I express that in terms of day 2 in the exponent? Well, 2 minus 1 as an exponent. And I'm beginning to see a pattern. Does that hold in 3? Well, I can write day 3's profit as 3 squared, which in terms of day 3 is 3 to the 3 minus 1 exponent. And now I definitely see a pattern. And while I can't say for sure the exact amount that I would get on the nth day, a generic day, I can write the exponential expression for it as just 3 to the n minus 1 exponent. All right, well now our mission is clear. What we want to do is we want to see for what value of n will this value exceed the value of the car. Well, how can I do that? Well, the value of the car is $25,000. On day n, I'm getting 3 to the n minus 1 cents. So the first thing I've got to do is correctly figure out how many cents there are in the value of that car. Well, that's pretty easy to do because we know that 100 cents make up $1. And so what I see here is that $25,000 is the same thing as 2.5 million cents. That's a lot of cents. Or in scientific notation, 2.5 times 10 to the 6. All right, so our mission now, I think, is clear. What we want to know is what is the value for n so that this amount exceeds or is greater than or equal to that amount. That's the question. So let's write that down. So our question now is to determine when 3 to the n minus 1 exponent exceeds or is greater than 2.5 times 10 to the 6th power. Well, there's an inequality that we want to solve. And the problem is that the unknown is in the exponent. So I immediately will take logs of both sides. And what I see now is log of 3 to the n minus 1 is greater than log of 2.5 times 10 to the 6th. And now I can use the wonderful property about logs, which tell me that if I have log of something to a power, that exponent here comes out as a coefficient in front. That's the power of taking logs. So when I do that, I see, and I'm going to make a mistake now. See if you can figure out the mistake I'm making. I see n minus 1, there's the exponent, in front of the log 3, greater than log 2.5 times 10 to the 6th. Do you see the mistake I made? Well, what I do here, I want to multiply this entire exponent by log 3. But I'm not doing that. The way it's written, really what I'm saying is that that 1 is being multiplied by log 3, but nothing else is. To really make sure I multiply everything through by that log 3, I need to put parentheses around here. This is really important. If you were stumped by this, then what you should do is make a note, write it down in your notebook, and say, gotta remember, clump all that together with parentheses. Okay, so now what we want to do is we want to solve this for n. There are a lot of ways of doing this. I can divide both sides by log 3 first, just to get rid of the log 3. Now, it's an inequality. So we have to be careful, because if we divide or multiply both sides by a negative number, the sign, of course, is going to move in the other direction. So, is that a problem here? Well, no. If you type in log 3 on a calculator, you'd actually see that that value is positive, so we can divide through without worry of sign. So if I divide through, I'd see n minus 1 is greater than log of 2.5 times 10 to the 6th, all divided by log of 3. And now if I just add 1 to both sides, I see that n has to exceed log 2.5 times 10 to the 6th, all divided by log 3, plus the number 1. Now, using a calculator, we can actually estimate what this is, and we'd see 14.41 days. That's how many days. Now, I'm asked, the question is, how many days would we, on what day would we receive more than the value of the car? So the day has to be bigger than the 14th day, and so therefore it's the 15th day. So that means that on the 15th day of the prize, where you get a penny and then triple the previous day, on the 15th day, you're actually going to exceed, as your income for that day, more than the value of the $25,000 car. Absolutely surprising. By just starting with a penny and using exponential growth, it turns out in 15 days, the value you get on that day far exceeds $25,000. So, do you pick a $25,000 shiny automobile, or do you pick a penny? The answer, found by exponential functions and logarithms, is pick the penny.